session today. So the menu for today, we are going to continue with this Hysys exercise. I told you that you could try, if you have your laptop here, to try to follow it with me in class, because that's going to be one of the exercises. Then I'm going to do what I thought is that to make it simple initially, we're going to make a horizontal pipe, just like the same way we have done in Excel. And then I'm going to show you how to put the elevation, and I hope you do it later when you have to do the exercise, okay? So, but you get the idea how you have to set it up in Hysys. Then we're going to close this small discussion about flow assurance. I want to make kind of a summary table showing you the most important flow assurance issues, why these are originated, what kind of operational problems you can get, what is done in practice to tackle these flow assurance issues, and what kind of software or what kind of tool people use actually to analyze these issues. And with that, we close with flow assurance, and we close about also pressure and temperature. It's a big area, and there are still many things to talk about, but probably those of you who end up in flow assurance department or who end up in multi-phase flow department, you probably will have to, do a lot of catch-up. Then we are going to start talking about a bit about pumping, ESP. I guess some of you have some background, but just to give you some basic information about pumping, about pump design, how the operational envelope of the pump looks like, and because we will use that knowledge somehow a bit for when we have multi-phase boosters. Okay, and that's all. I hope I have time to go through it today. So we were on our exercise. We were actually the exercise was the pipeline that goes from a Snohvit field and carrying the production of gas with some liquid. This liquid is partly water that was saturated in the gas at reservoir conditions, and when you take it up and the temperature begins to reduce, then the water carrying capacity of the gas begins to reduce also. Okay, it's the same thing that happens in the windows in winter when the air close to the window becomes colder, and then the water begins to come out of the air, okay, and begins to wet the window. It's the same thing. So when it gets cooled, then water begins to condense and begins to drop out, and we get some liquid, and also we get some condensation because we have some also heavy components in the gas. So just to summarize what we have done so far is we first put all the components that we're going to use, okay, that was done in this tree menu on the left. Then we said how are we going to treat these components, and that was given actually the equation of state. What are we going to use to calculate? Then we went out of this tree, and then we went to the simulation environment, and then we create a material stream, which is something that is the input to a process. That in our case, our process will be the pipe. Okay, because remember that this simulator, it's a process simulator, so it works all the time in basis of input and output. Okay, so we created this input. We first we don't know exactly the pressure. That's one of the things that we want to calculate. But we said we gave an initial value. We obtained from the Excel file, we obtained 80, but we said, okay, it has some liquid, we are not capturing the multi-phase flow behavior so well, so we said 120. We will see just now in a few minutes if that was a good approximation or not. The temperature also came from other calculations. We have to assume the reservoir temperature, then we have temperature losses in the well. Okay, those of you who are taking natural gas, probably you know how to do it. And then you have flow in the flow line all the way to the phlegm, and the temperature, we assume we know it, is 67 degrees Celsius. After that, what we have done also, we put the molar rate, okay, and we could also put the mass rate, but we chose to put the molar rate. I told you how to find it. I think we have done that also last class. Okay, that's not good, it's empty. Maybe I didn't save it yesterday. Okay. Okay, we had the standard flow rate of oil and the standard flow rate of condensate, and then we said we had also the density at standard conditions. From there we can get the total mass flow rate, and then with the composition we can get the molecular weight of the mixture. Okay, and with the molecular weight and the total mass flow we could get from there the molar rate. Okay. I don't know what happened. Let me see if maybe there is some other place. I don't know. Okay, so we gave enough information, okay, and I told you also that you could create in attachments, you can do some other analysis to that stream. And one very useful analysis is to see how the envelope looks like, okay? The mystical envelope that everybody's drawing this line like that, but okay, where actually is it coming from? And that's how it looks like, and actually all of this is the dew point line, okay? And the pressure point that we are analyzing is 67 and 120 bar, someplace here. Okay, so it's actually it's in two phases. You have a mixture of liquid and vapor. Okay. And remember, when we go now on the pipe, I think we took a screenshot of that. Okay, we are departing from these conditions, 60, 70, 67, someplace here. We are departing from here, and as we progress in the pipe, the pressure is going to go down, and also the temperature is going to go down. So it's going to be something like this, okay? It will have different shape, might be a bit curved, okay? But you are just going to see that right now, until we reach the separator pressure. Then the separator pressure is, we said 30 bar, right? So it has to go even further down up to here. Oh, yeah. Okay, so this is PLEM pressure, and here we have separator pressure, and we don't know exactly the temperature, okay, but the sea temperature is, I think was 4 degrees Celsius in our problem. Six degrees Celsius, okay? So the temperature of the sea is 10, it's someplace here, okay? That's the temperature of the sea. So we will see also, that's also one question that I want to think about it. If the temperature at the outlet of the pipe, what is the minimum that it could get? Okay, is it the sea temperature, the minimum that it could get, or it can go even lower than the sea temperature? Okay, what do you think? Shouldn't be less. How many of you vote that shouldn't be less? Okay, and how many of you vote that it could be less than 6? And those of you taking natural gas, you're cheating because you already got the solution there. Okay, yeah, so let's see. Okay, so we were now in the phase, we are going to progress from upstream. Our most upstream point was this, okay, the PLEM, and then we are going to see, then to define the pipe, and this separator should be a solution, should be an output of this element, of this pipe, okay? And we had to give energy stream that we say, okay, how much heat is going to come out of this pipe, because something that is also coming out is heat that is being lost or is being exchanged with the environment. Okay, so we opened the pipe. I think here is where we left yesterday. Then we made the connection first, and then we checked here. We were a bit curious to see what does it have, and you see these are all our experts that I have. And I have actually Lex experts that Hysys is not really a program to do multi-phase flow calculations. Okay, it's a process program, so they are depending more or less that everything is going to be single phase. But of course, they want to give some to be attractive also for people doing this kind of analysis. So they give some options. So we are going to use for now Bex and Brill, but please note that Bex and Brill is not very accurate for, it was developed initially for vertical and horizontal data, and it's not very accurate for when we have changes in elevation and when we have inclined pipes. But we are going to use it anyhow, but you can select any multi-phase expert. Okay, here there are some things that we are going maybe to talk about them later. Emulsions. Then was this part that was sizing, where actually I'm going to give the size of the pipe, the length of the pipe, and if there is any change in elevation. But before going here, let's go to heat transfer. And heat transfer, I can say I have a heat loss, certain energy that I'm losing with the environment. Okay, but I'm going to use this option that is overall heat transfer coefficient. Okay, all of you know what this heat transfer coefficient is? Do all of you know? Yeah? No need to refresh, nothing? Or you want a bit small, quick refresher? You need? Okay. Let's do it very quickly. Okay, when we have a pipe, I'm going to save now, a bit traumatized that it didn't save. So when you have a pipe, a transportation pipe, you actually, usually you have also multiple layers, but I'm going to put only one insulation layer. Okay, and let's say this is the pipe wall. And you have really two important points, that one of them is the temperature of the fluid, that I'm saying that is the average temperature that the fluid has. Okay, it's the core of the fluid. And then you have one other temperature that is out here, that is the temperature of the ambient. Okay, that is the temperature if I'm at the bottom of the sea, is the temperature of the sea at that place, or if I'm going uphill, then the temperature might change. If I'm inside of the, let's say if I'm on the well, okay, I have my well, I have my reservoir, and I have my wellhead, then the temperature is not going to be constant, but actually the ambient temperature is going to have some gradient. Okay, and really what is dictating the heat transfer is the difference between these two temperatures, and there is some resistance in between these two temperatures. Okay, there is some resistance of the heat going from the fluid to the ambient. Okay, so we can define the heat. We are going to use Q. Okay, heat flowing from fluid to the ambient. Okay, and really the heat doesn't change. What is leaving the fluid here should be the same that the pipe is receiving, and should be the same that the environment is receiving. Okay, you have to have conservation of energy. It's not like it can disappear at some point. Okay, so for heat transfer in solids, okay, heat transfer in solids, we call that conduction. Okay, and that is expressed by the following expression. Well, actually we don't have first, that's conduction and heat transfer in liquids, okay, or in fluids, better, in fluids, that is called convection. Okay, and actually we have two kind of convection. One of them is the fluid is moving at a certain speed. Okay, so the fluid has some movement. In that case we call it forced convection. You're getting a flashback from your primary studies, I guess. And then you have natural convection. that is when just by the same heat transfer, for example, you have a plate that is very hot, okay, and then you have some fluid that is just still there on top of the plate, and just because of the change in density, all the fluid that is here, it becomes warmer, so the density becomes lighter and then begins to go up, and some fluid, cold fluid that is above, tends to displace that fluid, and then you have also some movement that is generated by the same heat transfer of the fluid. Okay, so in this case we have convection from the fluid to the pipe wall. Remember that we mentioned also last class that the pipe wall is probably not at the same temperature as the fluid. It might be, but probably not. It's a bit colder. So we have this Q is equal to H, okay? I, this we call it internal convection coefficient. Okay, then we have area, okay, that is the area actually that you have in contact with the fluid with the wall, okay, and you have then the temperature of the fluid minus the temperature of the wall, and that's how you quantify the heat transfer from the fluid to the wall. We're assuming that the temperature of the wall is T1. Okay, and this area, usually the area should be the perimeter, okay, of the pipe. So in that case, will be pi. How is the perimeter? Diameter 1. Is it like that? Pi times the diameter times the length of the pipe. Okay, but I can do this equation in terms of length. I can divide both sides, so I can calculate actually the heat transfer per unit of length. Okay, so I get rid of the length. Now the same heat transfer, now if I proceed forward the same heat, I can also do an equation for the conduction in a solid. Because I have to flow, now the heat has to pass through the metal, okay, through the thickness of the steel thickness of the pipe. In that case, the equation is given by times L T1 minus T2, T2 assuming that is the temperature at this point, 1 over ln of R2 over R1. And that's how I estimate the heat transfer. Then again, I come from T2 to T3, that is the outer temperature, the temperature that if I touch the insulation, if I touch the pipe, the outer part. Actually, here I forgot to show it yesterday. This is a company is in Orkanger, just here south, maybe 40-60 kilometers from Trondheim. And actually, you can see so they make these pipes there, and then they have a way to roll them in kind of in a coil. Okay, so they have, if you see it from above, they have a piece of coast, and they have a long corridor where they have some kind of wheels. Okay, they have some wheels, and they put the pipe on these wheels, and then the ship comes, and they take these pipes and begin to roll them up in some kind of how do you call this? Reel. A reel, yeah. Okay. And begins to roll them in, okay, until they have filled the maximum capacity, and then another ship comes by, and these boats are lately laying the pipe in the subsea systems. Okay, so if you want to take a look, that's just a cut of a piece of pipe, and it's very nice. Those of you in the summer, maybe now it's too cold, that you have time, you can just go and with the car you park on the side, and you can see from there how the people are mounting the pipes and just mounting the pipes, and you can see, yeah, all the process.
What are the other layers?
Insulation. Just the two layers. The inner layers are to create to stick it to the pipe wall, and the outer is just for protection. And really what is doing the insulation is the white one that you see in the middle, okay? Because usually structurally that's not very strong. So if you leave that by itself, it might break, it might just get detached from the pipe wall. So you put these two for protection and for the integrity of the inner layer, okay? But as you see on the picture, I think I showed you yesterday a picture. Okay, you might have actually more and more layers, but then the pipe becomes bigger and becomes more and more expensive. And one thing important to note is that the density of this material is actually lighter than water. Okay, so when you put these pipes, well, if you leave them without any support, they will tend just to float, to go up. So you have to put some concrete supports to add weight to the pipe. Okay. Usually also what is also done is that instead of putting some plastic insulation, they also do the insulation with cement. Okay. You had any course about pipe laying and pipeline before? Any guest lecturer came and gave you some? No. Okay. Is the barge, and then the same barge goes, and when they're going to lie down, they have the C button, okay, and exactly the same, but now the reel is just okay, just unwrapping the pipe to the C button. Okay, so then conduction we have here. So we have in convection we have an internal H coefficient that is actually quite high inside the pipe. Yes.
What was the K?
K is called the conductivity of the material. Okay. Conductivity.
Heat conductivity.
Yeah, it's the thermal conductivity. Okay. And you have to check the units. Okay, that's so for example the H has to be given in watts. Remember that this heat is given in watts. Okay, so we have square meters because this is an area. This is in square meters times degrees Celsius. Okay, or degrees Kelvin. And conductivity has some different units. Okay. And this number usually, if it's very high for the same temperature difference, that means that you have higher heat transfer. Okay, so usually and you can see intuitively that the fluid, the H inside of the pipe, because it's flowing at high speed, so the speed helps for the heat transfer process. So usually the H inside is much higher than the H outside. Outside the fluid is still, you have some marine currents, but they really don't go as fast as the fluid inside the pipe, so the heat transfer outside is a bit less. But the thing is that you have a bigger area. Okay. Then we have, so if we do, let's say that we have only these 3 layers, okay? Each we have, let's say that we are going to neglect the heat transfer here. We have only the insulation. That is going to be an equation just like this, but with different conductivity. Okay. And then we have the heat outside. We have also the same equation, Q equal to H out times A out, T, how did I call the temperature? T3 minus T ambient. Okay. And then what I can do is just to add up all of these expressions. Okay. So if I add up all of these expressions, what do I get? I get all the equations. You get Q 1 over H internal A plus 1 over H external O and A external plus ln of R2 over R1 2 pi KL plus ln of R3 over R2. Okay, this is assuming only the metal thickness layer and then the insulation layer. 2 pi k, so this is k from the metal and this is k from the insulation, times L, and that's equal to Tf minus T of the environment. Okay, and now if you can also say that this is equal to, usually you want to represent, instead of having to carry all the time with the conductivity of each layer, with the convection coefficient of each, external and internal, what sometimes is done is that you say, okay, there is one coefficient called U that is the universal heat transfer coefficient, and the reference area that I use for that is the outer area, okay, the outer area of the pipe. Well, actually it's not like this, but it's 1 over, okay, 1 over I want to use just a unique coefficient, instead of carrying all the convection, because it might be different in different places in the pipe, and all of these insulation case and all the difference between the radius and everything. I just say there is one coefficient that if I multiply it times the external area of the pipe and times the difference in temperatures, I will get exactly the same that if I compound all the heat transfer in all the layers. Okay, so if you put these two equations together, at the end it tells you that 1 over U universal heat transfer coefficient times A, the external area of the pipe, is just equal to this big okay. And if you have more and more layers, like we showed on the last class, okay, we have more and more layers, more and more small, that doesn't matter. You just add them up because it's just another conduction layer, usually we have only 2 convection and all the rest are conduction. Conduction. Okay, and that's what we call the universal heat transfer coefficient. Okay, I think I have another expression here. Okay, 1 over actually is okay. Actually, this is also minus 1. Okay. Now, one question that I have to you: how do you do in this case? Do the same equations apply? Any ideas? Okay, these equations we were able to apply them because it's just using the shape of the pipe. Where is it? Okay, they are concentric, and we have the flow, the heat transfer in a way is radial. Okay, it's just flowing radial. That's why we were able to do all of these simplifications. Okay, but like you see in this case, that's not the case. We have a lot of things and we don't have actually uniform layers in between. So that's, for that we leave it to the more advanced people in heat transfer. Maybe a PhD will do his project about it. Okay, so short on that, and the values that I have provided on the Excel file, we are giving 3 values. Okay, one of them 5 is a value that is quite realistic. It's something that you can get with this insulation that I gave you. 5, 4, 3 is something that is quite realistic. 1.5 is already one value that is very low. that means that you have to pay a lot of money to get at least, maybe you will have a very bulky, or you have a lot of layers of insulation, which is not very practical for transportation, for flotation, etc. Or you have to pay for very good materials that they really keep very well the heat. And 0.5 is something that it can be achievable, but if you use, instead of using any insulation, you just use vacuum. Okay, that's a new technology that Technip is working on. And basically you have one pipe, and then you have an outer pipe. Okay, and there is just some supports to keep them centered, and in between them there is just vacuum, nothing. Okay, very expensive, but you can achieve very low heat transfer coefficient. So we're going to use 5, but in the homework you have to actually try with all of them and see what is the difference between them. Okay, so let's so we are giving the temperature at the sea we need, that's the ambient temperature. Now we have the inner diameter of the pipe, the outer diameter of the pipe, and we are going to use 5 as heat transfer, overall heat transfer coefficient. Remember also that probably H is a function of distance. Okay, why? Because when you move in the pipe, then the gas is expanding. Okay, if the gas is expanding, it's going quicker. Okay, so you might have some more heat transfer, or the U could be slightly bigger by the end of the pipe than at the beginning of the pipe. Okay, but we are going to neglect that dependence. Okay, we are saying it's not dependent on distance. Okay, so let's go and see what Hysys is asking. So it's asking for overall heat transfer coefficient, that big explanation just to show you what to put here. And the ambient temperature, how much was it? 6 degrees Celsius. That's exactly okay. Okay, based on outer diameter. That's exactly what we want, what I told you. So the value is 5. And here you have to be careful because it's kilojoule per hour. And we said that we gave that in watts. And watt is a joule per second. Okay, so we have to find the right units here. And it changed to its own units. That's okay. Okay, so now we have done that, and we go back to sizing. And now we are going to put the segments. I'm going to put now first, I'm going to put a horizontal segment, and then I'm going to show you just how you put the elevation, but then you continue doing that at home. Okay? Yes?
Did you choose per second?
Because that's the default unit, but when I select watts, I mean when I give the input, I say 5, and then I select the unit, that's going to be, the input is going to be in watts per square meter degrees Celsius, and then it's going to convert automatically to its own units. Okay? If you don't like that, you can go here, home, units, okay, and you can actually change and customize the units that you want. Okay, you can change it to bar, yeah, whatever you want. Okay, so let's say append segments, and in segment is a pipe segment, length, it was 158 kilometers. Okay, so let's put that 158, and we can select here kilometers. Elevation change, we are going to say initially is horizontal. Outer diameter, how much was it?
30 inch.
How much? 20?
30 inch.
30 inch? Sure.
Yeah.
Okay. I believe you then. 30 inch. Inner diameter? 26.7? Okay, roughness, we leave all of that. Usually the roughness depends on the diameter, and that in many programs is already given as an input for you, because that depends on the mill. When they do manufacture the pipe in a certain size, they can guarantee certain roughness of the pipe. Okay, there is a standard roughness depending on the type of steel that you are using and the manufacturing process. Pipe wall conductivity, what is that? The K, if you remember what we just saw, so it's 45, And remember, if it's higher, it means that you have high heat transfer, okay, which is obvious because you have is metal. And here there is something very important, that is number of increments. What is that? The discretization that we are going to have used in the pipe. So in this case, it's using 158 kilometers divided by 5 step. That sounds like too much, okay? Why is that important? Remember that we're going to use average properties in each pipe segment, okay? And if we choose the segment very large, the property that we use is not going to represent very well all the variation that you have inside, okay? So let's use, maybe we can use 1,000, and that will give us roughly a section of one. Yeah, is that correct in kilometers? Yeah. Okay, 158 meters. Which, okay, I say it's okay. Okay, and if you see now, it said okay, it had enough information to run. So let's see what it calculated for us. What is the pressure here? Oh, you see surprise? You see the temperature?
Yeah,
-2. Okay, why is that?
Because section is low.
Yeah, not really.
Thompson.
Okay, Joule-Thomson effect. Anybody of you heard of that? That happens only when you have gas, okay, or you have a fluid that is mainly gas. It's because when the pressure goes down, you have also an effect, a cooling effect. It's when you pass, I'm not sure if you have had also that experience in processing, but when you pass a gas through a valve that you have a pressure drop, also the temperature is going down. Okay? It's exactly the same principle. When the pressure goes down along the pipe, that causes also that the temperature will drop. Okay? And it's called Joule-Thomson effect. I'm going to put it written later. But you see, something that we don't like too much is that the pressure at the outlet is 47. That means that the pressure that I put here was too high. This 120 bar was too high. I should get here exactly 30 bar. So how do I do that? I could change it manually, for example. I could say here is 115 bar. Okay, 26. I already went too much, only by changing 5 bar. So really what you want to do in the industry is not to be putting numbers one by one, because otherwise you spend your whole morning and then you cannot do anything else. Okay, you want to go home early. So for that we're going to use some kind of solver. Okay, if we had the same problem in Excel, what do we use? Solver. We say solver, please put this pressure here to 30 by changing this pressure, right? That's what will you do in solver. Luckily also Hysys has a solver that is called adjust. And adjust you can find in the palette. It has this wrench, okay? And in the adjust we say exactly like in the solver, we have an object, something that we want to get to a certain value. Okay, so let's see, we have to select, and that's separator, and we go and look for the property. It's called pressure. Okay, and no, actually that's the adjusted. Okay, so what I'm going to adjust, the pressure in the plem. Okay, the plem exactly the same, and the object is the pressure at the separator at the end of the pipe. Pressure. And how much do I want it to be? 30 bar. Okay, and it says unknown maximum. Like the solver, this solver is very sensitive. Okay, so we have to do some customization in the solving parameters. So we go here to parameters, and yeah, but that's optional. That's minimum and maximum of the adjusted variable. how much do you want to try? I wanted to try 120. For example, can I try 300 bar or 400 bar? If you already know that your maximum pressure is the reservoir pressure, you know what is your upper limit. Okay, you know that you cannot put more than that. But let's leave it. I don't think that should complain because of that. I just click start. Okay, and you see here is changing. Okay, changing, that's the, okay, it got exactly to 30.001 bar. Okay, it took some iterations. How many iterations? 11 iterations. And the tolerance, this is how much I want it to be close to 30 bar. Okay, in this case 30 plus, yeah, 0, 0, exactly this tolerance here, 0, 0, 1. Okay, I want it to be, let me just copy that. Okay, this I'm saying that I want to be P equal 30 bar plus minus 0.001 bar. I want it to be within that range. Okay, this is the P at the plem. Okay, what is the minimum value that I can try? We can put 30, even it won't make any difference. And P plem, what is the maximum pressure value that I want to try? And I can say, for example, reservoir pressure. Okay, but that's really just to give a bound. And the maximum number of iterations I can increase, of course, if maybe after some time it doesn't manage to find a solution, I can just increase and it will have more time to find the solution. It will have more iterations to find the solution. And this step size is the changes that it's going to make in plem. Okay, in this case is 10, is actually quite low. It can try, for example, 120 bar, or you can try 120, 0.1, okay, bar. That's the changes that it's going to make in the adjusted variable to get exactly 30 bar. So you see that was actually a bit too small. Okay, if we could, for example, put 100 kilopascals, that will be, I think, or 50, that will be a better value. Yeah, any questions so far? No? Okay, now something very interesting is that you can, on the pipe, after it's solved, you can see on performance. Okay, and you can see on this button, you can view profile. I hope it doesn't crash. Okay, and you get all the information, and actually this table you can copy and paste it in Excel for further analysis. And you see length, of course there is no change in elevation. What is the pressure and temperature in each particular place? What is the vapor fraction? So you can see exactly what is happening with the fluid. You can see how much has been transferred per meter. Okay, I told you that the heat we usually divide by length of pipe. We have the flow regime. What do we have in the pipe? And we have just segregated flow. Okay, that means just a stratified flow. We have the hold up, that you already know what it is. We have the friction gradient, yeah, and some other very useful information. But maybe a better way to visualize that is you go here to plot, and first elevation. There is no change of elevation in the pipe, but we want to see how the temperature is doing. It goes from 67 down to -7 actually. Okay, so it actually goes way below the seat temperature. Okay, the seat temperature is I think someplace here. Temperature of the sea, and we see that actually goes below sea temperature. And this is due to the Joule-Thomson effect. Okay, that is when there is a change in pressure, when there is a delta P, a pressure drop, then there is, for gas, there is usually a delta T. Okay, there is usually a reduction in temperature. And there is a coefficient that gives you that relationship between delta P and delta T. That is called the Joule-Thomson coefficient. I can put the equation later. Joule-Thomson. So you see that at this point, actually in the pipe is getting cooled. Okay, it's actually getting colder and colder. But at this point, actually, what happens with the environment? The heat is going on the opposite direction. It's going from the environment inside of the pipe. It's actually heating the fluid. Okay. Now, so we are almost finished with that. So I'm just going to show you, because we want to make one last plot that is the phase envelope, P and T. And we want to see how is the evolution of the line in the phase envelope. So I'm going to show you some tricks how to get that value from Hysys, and then we just try to close the flow assurance part. Okay. Before we go to the break, any question? No? Okay, let's take a break. I think I for some reason the notes were not saved for yesterday, so sorry about it. If anybody has some nice notes, then can give them to me. I can scan them and put them in replacement of my notes, if you want. But good that we have the video. That's why you need to have redundancy. If something fails, then you have a second system. So just to show you also where this company that I gave you the pipe, where they are located, here we are in Trondheim, so you continue a bit south through the E6, and then you take E39 and you see here in Orkanger. And actually what I was telling you here, you can see from here you have the place where they manufacture the pipes. They leave them in long sections, straight sections. I think this is some 2 kilometers or something length. And then they weld them, okay, and then the barge comes here and begins to reel them in the reel. Okay, so what I was saying, if you have time, actually it's quite nice to take a bath. There is some nice beaches someplace here. Okay, you can take a swim. So you come with the car, with the bus. No, not joking, I have done it last summer. So you can go and park here someplace, and you can just enjoy an engineering spectacle of people loading all the pipes, and okay, if you're lucky. Okay, probably you want to do some better things in summer, but okay, so that's a Joule-Thomson coefficient. It's a coefficient that tells you the variation of temperature with pressure. And usually if you are formal and you do the derivation of the equations of flow of gas, with assuming energy and also momentum equation, you will get that coefficient that comes out in some place in the equation. And it's very important for the particular, especially for gas. Okay, one comment on Hysys. So on Hysys you can, so you click on the pipe performance profile, and actually you can copy whatever you want. So it's all the time nice. It's nice that you can plot it from Hysys, but also it's even nicer that if you copy the whole data and you put it in Excel, okay? Because Excel we can I thought that if you select it here, okay, it's kind of slow. Come on. Well, you can if you have patience. We don't have patience in class. You can select all the range of numbers and you can compute something that is very interesting to see. The hold up. I think I might have some pictures from previous course. That might be here. We're going to take the answer from the assistant. She's not going to be too happy, but probably she doesn't watch the video, so no problems. Okay. So here you see the temperature, the same case that we have done, and this is for an insulation of 5. Exactly the same. You put it in Excel, and you can control very nice the color, and you can put the 3 cases in the same file. And you see something interesting, that the hold up, depending on the length, that first is increasing. So why do you think is that? Why the hold up is increasing and then decreasing? Is having this shape. If any of you remember what the hold up is, that's the first question. Huh?
Liquid fraction.
Okay, hold up is if we cut the pipe or we have multi-phase flow, is the space occupied in the cross section by the liquid. You have to have at least that concept clear. Okay, I don't care if you don't know about sleep, but you have to know what hold up is. Okay, hold up, if I have my pipe and I have liquid and gas, so the hold up is the area of liquid divided by the total cross section area of the pipe. Okay, that's the hold up. So if it's increasing, it means that if it's doing that behavior, okay, it's doing something like this, what could it be indicating? You know, otherwise we leave it for the homework, and then you have to explain. You will have to explain anyhow, so better to do it in class than... Why the hold up might be increasing?
Condensation.
Okay, that's one thing. I just have more liquid, okay, and there is liquid coming out of someplace. So maybe here what's happening if I have condensation. And how can I verify that?
But if your condensation pressure will decrease, right?
Yeah, the pressure is going down.
Then
That's just the hold up.
temperature will go down.
Yeah, the pressure, I think she plotted the pressure someplace. Okay, the pressure is just going down all the time. Okay. So how can we verify if this liquid hold up is because of condensation or not? We can check at the phase envelope, right? And if, remember in the phase envelope, we have something called quality lines. You remember that? Yeah, from your old, okay. You have some lines that you have. Here you have actually 90% vapor, and here you have 80% vapor. Okay, quality lines, equal quality lines. So if the point that I'm analyzing in the pipe goes in this direction, it means that all the time the liquid fraction is going to be increased. All of you know what quality is, or remember what quality is? Quality equal to mass of gas is a mass fraction of gas divided by mass of liquid plus mass of gas. Okay, so if the quality is 1, it means that I have pure gas, and if it's 0, it means that I have pure liquid. Okay, so these are these lines. When I get 100% gas is the dew point line. This is the dew line actually. And when I enter into the envelope, I will have some liquid condensing, and then I will have more and more liquid, so the quality will go down on this direction. X will go down. Well, actually it's not an X, but it's kind of a Greek X. Okay. So might be one explanation is, okay, might be because I'm getting just more liquid, and that's a feasible explanation. So what's happening here? Why again it goes back down? What might be happening in this case? Hmm?
It is vaporization.
Might be. Could it be that it's revaporizing again?
And maybe due to blockchain. But in that case, pressure will increase.
What happens if I think I have? Maybe we have. Okay, so that's one explanation. Okay, just condensation. And here, one explanation that was given is that is evaporation. Okay, but you are missing something. How else could the holdup be changing? Because of what? Just because of the dynamics of the multiphase flow, right? Just because the liquid begins to go slower than the gas, right? That means that the velocity of the liquid, it begins to go down compared to the velocity of the gas. Okay? That means the gas is flowing quicker. Then as the gas is flowing quicker, it requires less cross section. Okay? So the liquid layer begins to go up. Okay? That could be also an option. But what is a bit suspicious about this case is that depends, I told you, multiphase flow depends on many things, okay? But it depends also on the inclination of the pipe, right? If I have the pipe going up, then the gas will tend to go quicker than the liquid. I have the pipe go down, okay? And in this case, how is the pipe? Horizontal, okay? So really, if I have an effect that one phase is going quicker than the other, I'm not so sure that that's the explanation, okay? But you have to think about that also when you think about why the holdup is doing that, okay? So let's now see, and with that we finish this exercise, not the class.
So, in this case, what is the explanation?
Yeah, we go for the phase envelope to get more answers, okay? We don't know yet. We suspect it's because of condensation, and then you have some evaporation, okay? Like, what happens if let's say, I manage to get the temperature constant, okay? And I have a point going here. What will happen if I take point from 1 to 2? What will happen? Retrograde condensation, okay? That means initially here was all vapor. When I first get to this line, I will get the first droplets of liquid, okay, coming out of the gas, okay? Then I have more and more liquid up to this point, and then again it's going to go back in the quality lines, and the quality is going to increase until I have only vapor again. That's called retrograde condensation. And that I have condensation, okay? Then I have evaporation. Okay? So maybe something is happening like that here. Maybe I'm somehow going back, I have a point, and then it's kind of returning back to crossing the same quality line, okay? But for that we need to see at the phase envelope. So again, I'm not going to do it because it will take a lot of time. I'm just going to show you how to extract the data. Okay, so you see here that you can actually copy, but you have to be patient to select the whole range. I think before there was a way to copy the whole column by clicking here. But I don't think that we can do it. So you can just copy, and in an Excel, I just paste it. And I can extract all the data from from Hysys to Excel, and then I can use it much simpler. I want to plot the phase envelope. So for the phase envelope, I go to the utility where I have the phase envelope. That will be here. How is going to be the phase envelope? Does it matter if I choose this stream or this stream? Should they have the same phase envelope? Huh? Exactly, because they have the same composition, okay? I'm not adding mass here. I'm not changing the composition. There is no reaction. So it should have the same composition. So I'm going to choose the inlet, attachments, analysis, view, the envelope. And actually here I can go on the table. You see here on the left I have table. And I can get, if I select the dew point, I get all the combination of pressure and temperature that define this blue line. Okay, so I can copy. Not behaving very well. You see the kind of issues that you will have, so don't laugh, because karma comes back all the time to bite you. Okay, so I have P and T, and remember we want to put units, so that's in degrees Celsius. That's in actually kilopascals, and this is in degrees Celsius, and we plot these two. Okay, and you get the chart that we already knew. Actually, this is shifted. It should have the temperature in the X and the pressure in the Y. Okay, and from here we can get our phase envelope. Actually, I can also plot the quality lines, because that's what you want to see, the quality lines. So the quality lines, I have to go back. I haven't defined them yet. Okay, quality 1 and quality 2, they will be empty, but I can define in here in the plot. I can say the quality line 1 is 0.01 and 0.02. okay, and then they will be plotted, and then on the table they will appear. So I can actually take them from here and plot them the same way I have done with the due line. Okay, and after that I can also take the collection of points P and T and plot them on the same plot to see how is the evolution in the pipe. And that, let's see if we go back to the work of Anna. Okay, that's how it looks like. Okay, she actually did extracted for 1%, 2, 3, 4, 5. Okay, and we go to the case, to the isolation that we are analyzing, that is 5, is this red line. And you see exactly that at some point here we have condensation, okay, all the time the quality is increasing, okay, so we have condensation, but then at some point there comes a point where I get maximum quality, and then it begins to go back, okay. And actually here is where I have this evaporation. Here from this, in this part, from this point to this point, actually the amount of liquid is decreasing. The liquid is getting re-evaporated. Okay, so here I have this retrograde, actually she put it there, retrograde condensation areas. Okay, so in that case you can say with some safety that the increase in holdup is because of I'm getting more and more liquid, and then the liquid is evaporating a little bit. Okay, that clear? Yep. Okay, so that's, you are going to get that as an exercise. I hope I have already saved a lot of work that you have to do by doing it in class, so I hope that you can do it fairly quick. And you have to run sensitivity on the different insulations and see what is the difference in the inlet pressure. You see that the pressure is different, so why is that? Why do you think the inlet pressure is different for the different insulations? Okay, remember that delta P is a function of, or that I have two components. I have the gravitational, okay, gravitational plus the frictional loss. Okay, this one depends on the velocity, and the velocity depends on the density that I have, and this one also depends on the density. Okay, and density is affected. Density is a function both of pressure and temperature. Okay, so if the temperature is being lost at a different rate, if at the different points in the pipe I have a different temperature, that means that I will have a different density at that position in the pipe. That means that I will have different gravitational and different frictional losses. Okay, in this case it's just horizontal pipe, so the component will be mainly frictional. Okay. Okay, any question? Suggestion? Yeah.
The P inlet is the P plem, right?
Yeah, this is P plem.
And it is different.
Well, because we are calculating P plem. Okay.
Oh, yeah.
In reality, you will have only one, depending on the insulation that you have. Okay. If you choose for probably, I think this is a Snohvit. It's using 1.5, so probably your plem will be the green point. Okay. You will have a unique solution, but this is just telling you how it changes with kind of insulation you're using. Okay. No sweat. Easy. How to say easy peasy. I think you feel a vacuum. I see your faces and you are kind of missing something. You need an exercise. It's coming. No problem. I look and you're looking at the horizon like, oh, we don't have any exercise. So what should we do now with our life? So no worry, it's coming. No, don't worry. Okay, so now just to finalize, let's make a table summarizing the flow assurance issues that we have discussed. And I'm going to put, okay, so flow assurance issue. Let me just put it small so it will fit. I think I have to write a bit. Okay, one thing before I forgot. When you have the elevation, remember that you will have some sections that go up and down, up and down. What do you think will happen with the hold up in the sections going upwards and in the section going downwards?
Upwards and decrease.
Okay, it's going to decrease. So you will see a change in hold up that goes together with the change in inclination, okay, of the pipe. Keep it in mind because some people, they come afraid and they say there is something wrong. It's kind of flipping up and down, and that's just because of the dynamics of multi-phase flow. Okay, remember, hold up comes affected by two things: the PVT, condensation evaporation mechanisms, and the dynamics of the multi-phase flow. Okay, flow assurance issue, and we are going to put then we are going to put a picture, okay, or we can put it right away. Then we have the cause, or how does it, originate. Then we are going to say the consequences, what kind of things that flow assurance issue can bring, consequences. Okay, then what kind of solutions does the industry is using or is applying? Industry solutions. Industrial solutions. Okay, and then we need I want to put also a comment about the tool to analyze. Okay, what kind of tools do we use, or what kind of expertise people that work on that particular issue they need to develop or they need to have. So we are going to, I think I have too little space, but let's see. Okay, so first we are going to start with hydrates. I think we had a nice figure or picture of hydrates someplace. Okay. Okay, what causes hydrates? Hydrates, okay, It's a kind of a nice. We said that it causes because the molecules of water, they arrange in some kind of solid pattern. Okay, it's kind of a box where the light molecules, light hydrocarbon molecules, they want to go inside and keep it stable. Okay, it's kind of a nice form with water and also with hydrocarbon molecules. So, what do you need to form hydrates? Okay, you need water. And can it be in liquid form, or it has to be liquid or vapor form? Huh?
Free.
It has to be free water. Okay, it has to be liquid. So if you have water that is just vaporizing the gas, there is no issue. But when there is condensation, that the water comes down, it condenses, then you might have hydrate problems. So free water, you need to have free water. Okay, in liquid form. Then you have to have light hydrocarbon molecules. Okay, remember that these molecules, they want to be inside this box, so they have to be small enough to fit and to be comfortable. If it's a big chain, a big molecule, usually you don't get formation of hydrates. Okay, then you have begin to form at a certain P and T. Okay, that's, I told you, more or less it's like flash calculations. Okay, it's the equilibrium of liquid and gas. Okay, you have an equilibrium of solid and liquid. Okay, begin to form at P and T according to hydrate equilibrium. Okay, and I think here I have to put some more space. Okay, and here we can put, actually we had a plot from last class that we discussed a bit. Okay, you have a line that might be a bit too small, I think. Okay, you have a line P and T, and that defines a region where you are safe, you can operate, no problem, and then you have a region where you might have formation of hydrates. Okay, and the mechanism of formation is, you first have the formation of these small crystals that we call precipitation. Okay, of the crystals of hydrate. Then we have agglomeration. These crystals begin to attach one to each other, agglomeration. Okay, precipitation and then agglomeration, and then you have problems. What kind of consequences do we get with hydrates?
Blockage.
Just blockage of the pipe blockage. Okay, and then we have all issues related with blockage of pipe. Loss of production, we have to restart production, we have to find a way to remove this block. And yeah, it's not so simple when we are talking about a pipeline, for example, of 158 kilometers. If that happens, yeah, then we are in a big problem. Production loss. Okay, let me put more space here. Okay, industrial solutions to hydrates, or industrial, let's say, preventive measures. Okay, really with flow assurance, it's better all the time to take a preventive strategy. You don't want that the issue arises and then you are taking some hot measures to counterbalance. So this really should be preventive measures. Okay, and these are industrial because it's what people are using. Okay, so what kind of measures could we use? Okay, So you can take this line and you can try to operate all the time on the right. How do you do that? You make sure that the temperature doesn't fall inside of the area. Okay? So pipe insulation. Okay? You try to keep the heat. Another way to keep the temperature up, what is it? Heating, electrical heating. But if you have a very long pipe, 20 kilometers or something else, if you put a heater, then someone is going to, tell you that's too expensive. We cannot be paying for that. Electrical. Okay. We can inject something, hydrate inhibitor. Okay. That basically is going to move that line further to the left. Okay. Basically, what we say is that we are expanding our operational region. That's what happens when I inject an inhibitor. And the inhibitor is really, the inhibitor that's very important is acting on the water, is acting on the free water. Avoiding, just giving enough space between molecules is kind of diluting the water in a way that it cannot form these crystals. Okay? So there is something very important here, that the temperature, this inhibitor usually has also, if you increase too much the temperature, is going to evaporate and it's going to become part of the gas. Okay? And if that happens, you don't get any more protection. Okay? Because it's exactly like the condensate. It can condensate at a certain temperature, but if you increase too much, it's going to evaporate. And then you lose it from the water, and then you might have hydrate problems. Okay? So acting on the free water, that's very important. Avoid, well, I'm going to put it in red. Avoid inhibitor evaporation. Okay, that's typically 150 degrees Celsius. It's a typical inhibitor evaporation temperature. So we want to keep the temperature in the pipeline all the time less than 150. Okay, to avoid evaporation. Because if it goes to the gas and it becomes vapor, then it stops protecting anymore. Okay, and we are completely unprotected against hydrates. So you think, where could I get an increase in temperature? You're saying that we lose temperature, so where could I get an increase in temperature? Compressors, okay, that's very right. In compressors, as you will see later, we will have another session. When you increase the pressure, also the temperature is increasing, and sometimes you may get that you get close to these ranges, and then you get evaporation of the glycol, evaporation of the methanol, and you might begin to have problems, issues. Yep.
In compressors, we usually don't want the liquid fraction.
Yep. But we have wet gas compressions, for example. There are now a lot of, for example, in Snohvit, they are going to install a wet gas compressor in 2020. It's already in place in Gulfax. So there is a technology to compress liquid multiphase mixtures. Okay.
So it's actually compressing.
But actually, also it happens if you split. Let's say you have liquid, okay? You have liquid going down and then gas, and then you put a compressor, dry compressor, and then you put a pump, and then you merge them. If this temperature for some reason goes greater than 150, when you mix them, probably the temperature of the mixture combined is going to be greater than 150. So you might have this risk of evaporation. Okay? So one way to avoid that is just maybe to put a cooler, okay, before the compressor, and you cool a bit you won't have hydrates because you have inhibitor anyhow. Okay. So it's just to protect the inhibitor. What else do we have? We have thermal insulation, electrical heating, chemical inhibitor. There is also called cold flow. I'm not sure if you have heard of it. It's people say that the main issue is, like you said, it's not like you see here. It's not the precipitation of the hydrate, okay? It's not the formation of the hydrate, but it's actually the agglomeration that they tend to stick together, and that's where the problem causes. So some people go to the approach that they say we're going to induce hydrates, but we are going to avoid agglomeration, and we are going to transport it in some kind of a slurry. If a bunch of solid particles, okay, that will be a bunch of solid particles of hydrate, okay, just like a slushy, okay, like this thing that you drink in summer when you are thirsty and you are, you want a refreshing drink, okay. You have particles of hydrates mixed in the flow, okay. But the question is how then you avoid that they agglomerate. Okay, and you can put also inject some substances. So that's something that is in development. Actually, it's a concept proposed by Sintef, and maybe we will see more of that in the future. Okay, but basically say I don't have problems with hydrate forming, but I want that they don't agglomerate. Okay, and I find a way to avoid agglomeration. And also one other solution that we are kind of neglecting is water separation. And that's a trend now. If we manage, for the fluid that comes from the well, if I manage to separate all the water, then I will be problem free. I don't have any more hydrate problem, right? Okay, but that's also some technology that might be coming in the future, but currently it's kind of not in use. Okay. And also remember that the water not all the time, as I explained before, is not all the time in liquid form, but it might condense along the pipe. So you separate it at some point, and then as the temperature drops, you are going to get water that is condensing. So you still might have the problem. So you need really a kind of a subsea drying process of the gas. Yeah, here tool to analyze hydrates. Usually you can use, as I told you, correlations. If you have a gas that is very similar to the correlation that was developed, that works quite okay. But usually you use a compositional simulator, a compositional and multi-phase simulator. Okay, the multi-phase simulator, you use it to see how the pressure and temperature are going to change along with distance, and the compositional, you use it to see the equilibrium, when the hydrates are going to be in equilibrium, when you will have the formation of these hydrate structures. And in Hysys, I think we can go very quickly. I think it should be here. No. I think I have to add, let's see. Okay, hydrate formation. You have one in the same place where you had the envelope. You have, again, something called hydrate formation. And you can see if at that pressure and temperature you will have formation of hydrates or not. Okay? Let's see if here we have. Okay, will form, but where do we get the? Okay, here you have at that stream, at yeah, let's take that plot. Hydrate formation is called hydrate formation module in Hysys, and okay, so it's telling you at that particular pressure, that in that case I think we selected 30 bar, okay, pressure and temperature, okay, at that particular pressure of 30 bar you will get hydrates forming at 10 degrees C, okay, at 30 bar. And at that temperature, that was I think -7, was it? minus 7, so minus 7 is someplace here, minus 7 degrees C's. The pressure, formation pressure is, yeah, 5 bar, is it? Yeah, 5 bar. Okay, so you get 2 points in this hydrate line that goes like that. Okay, and there are different methods, different yeah, I think here you have the method that is using, that is called NG and Robinson. Okay, just a way to calculate the equilibrium of hydrates. Okay, and also you get some more information that we have no idea about it, but you, maybe one of you will get an expert and then will come and teach a class for me in the future. Okay, any question about hydrates? No? Okay, let's go very quickly to wax, I think. Also, one solution that people try to do is say that the coating somehow can help. Okay, pipe coating. Okay, you put something, a polymer in the pipe wall to help to avoid the formation, to avoid the agglomeration of the hydrate. Okay, so we got that here, and now we go for wax. We had a picture of wax here, this guy, that he's happy. Okay, and basically the wax, it's also precipitation of heavy chains. Has a solid phase. Okay. Then really, why does it appear? It's just that some crudes have the tendency, depending on their content on heavy components, they have just a natural tendency to produce wax. Crudes. Okay, and there is actually the same way like the hydrates have, there is actually a P&T combination that define a region where I will have wax formation and non-wax formation. So there is some kind of also a thermodynamic equilibrium of wax playing a role. Equilibrium, so to say, okay, a given P&T. Also, something very important about wax that we mentioned yesterday. Did I put the recording? Is remember that the wall has to be cold to it to stick to the wall. So cold wall. Okay, and when we say cold, it just has to be colder than the fluid, than the. And we have actually three phenomena. We have precipitation, we have agglomeration, and we have deposition. Okay, again, the people say it's not so dangerous that the crystal of wax appears, but the problem is when it sticks to the wall and then you have accumulation over time. Okay, what are the consequences of wax? Increased pressure drop. Okay, and the pressure drop increases due to two reasons. The roughness of the pipe increases. Okay, and also the cross-section area of the pipe is left untreated, is also going to reduce cross-section also, another problem is that you have gelling. Okay. That actually, as I told you yesterday, the wax, when it begins to cool down and you stop the system, begins to cool down, it behaves almost like a non-Newtonian fluid. And a particular non-Newtonian fluid that if you have to provide certain initial delta P in order to begin to flow. Otherwise, it's just like a plug in the pipe. And you have to provide certain push so it will start to flow. And that's what I'm saying by gelling. And that causes a problem in startup of pipe. Okay. Something that I forgot, maybe we can include another, well, no space here, but we say this happens in flow lines and pipelines. Okay, and yelling. Okay, so how do we cope, or what are some of the measures that people use for against waxes? Okay, we try to stay away from the P&T area, from the unsafe region. Stay away from wax region. And that really the only control that we have is pipe insulation. Okay, we can use electrical heating. We can use also chemical inhibitors. Okay, and we can use also, we can, let's say, okay, we can allow that the wax will deposit. Okay, but then we are going to put every certain time a chemical that is just going to dissolve this wax and make it flow again and make it dissolve, disperse, and we can take it with the flow. So we can use chemical dissolvers. Okay, and that's a very different concept that for hydrates. Okay, hydrates we cannot for any circumstance let it form. When it forms, it's going to block. When it blocks, we are in the hole. If there is a hole here, we are here, and there is no rope, anything. We cannot get out of it. Okay, so but for wax we can allow some deposition, and then we can try to inject some chemical to make the problem better. Also, a universal solution, and maybe I should have put it first, is pigging. Okay, usually we execute a combination of that. We put a good pipe insulation, we put the chemical inhibitor, and then on top we do pigging. And pigging really depends on the properties of the crude, but kind of not normal, but the common number is every 3 months. Okay, do pigging. What else? We have also pipe coating. Some people say that if they put certain coating in a specific with some properties, then the wax is not going to deposit, but it's just going to slide, and it's going to be carried by the main fluid. Okay, what is the problem with coating? Can you rely 100% on it? Remember that we mentioned yesterday another big problem that was erosion. Okay, we have erosion due to sand, due to bubbles, due to droplets. Okay, and this erosion, the typical case is that it's impinging in the walls and it's making holes, and what's happening with the coating? Okay, it goes away. So if you're relying all of your protection with waxes is a coating, and then the coating goes away, okay, you're not protected anymore. And there is also cold flow. Okay, some people that say the same technology used for wax, the people say, okay, let's form wax, but we are going to try to carry it now. We are going to avoid agglomeration, avoid sticking to the wall, and then we can carry it in the main. Yes?
It's about coating. So coating is outside, insulation is inside.
No, coating is inside of the pipe.
Inside.
Yep.
And what's the difference between insulation and
Coating, if you have your pipe like that, okay, coating goes here. It's a small layer that you put and you cover. You put it on top of in the inner part of the pipe. Insulation, like you saw on the thing that I passed, okay, is outside of the pipe. Okay. And how do we? So what kind of tools do we use to model? Really, there is no. You cannot trust in any there are many people trying to develop equations, equation of state. They use molecular simulators. They use all kind of things. But really, what people use and people trust to do wax is laboratory experiments. Okay, like for example, the case of Snohvit. They were concerned about hydrates, so they did chemical injection, injection of chemicals, of methanol, but there was no problem with wax, they weren't going to have any problem with wax, so that's why you have only one pipeline. If they, on the other side, will have wax problems, then they have to do two lines to do pigging, and maybe that would have been uneconomical. So they were lucky and no. Huh?
Do they use scratchers instead of pigging?
For long pipes, it's more practical pigging. And the pigs that they use usually is the pigs that there are different kind of pigs. I think I have a presentation. I'm going to upload this also to its learning. Okay, there are different kind of pigs. So the pigs, you have these soft pigs, almost like a cushion, and you have these hard pigs that these are usually the ones used to move the wax, because you have something that kind of scrapes a bit the wall. Laboratory experiments, and then you tune to correlations or expressions, and that really happens, like I told you yesterday, that happens after the wellhead, because usually the temperature is hot enough in the well, so you have these kind of issues in the flow lines, pipelines, etc. Okay, and what you try to get also from here is the deposition rate. Okay, that means what is the deposition or the mass transfer from the fluid to the solid, with versus temperature. How is it going to be when the when the temperature goes down? We have still some 3 to go, so I recommend I prefer just to take a break now, and one question before the break.
Yeah. So this is for one phase flow, right? For example, for oil. But if, for example, we have multi-phase.
No, you do it's on the oil phase, but you might have concurrent flow of gas and oil. And if you have water, you might have hydro formation with the gas, and you might have wax deposition with the oil. Luckily, usually the fluids that have wax, wax formation, they don't have so much problems with hydrates, and the fluids that have hydrates don't have too much problems with wax. But you might have both. You might be unlucky enough that you got both.
So the chance of wax formation is higher if we are transporting multi-phase due to Joule Thomson, right?
If the temperature, but if you have mainly oil, you don't have this Joule-Thomson effect. It's not so important. I mean, it's important, but it's not as important as for pure gas. It has to be kind of a rich gas or gas with a high content of liquid for it to be. When you have mostly oil, then this Joule-Thomson effect is not so important. Okay? Any more questions? We take a break, 10 minutes? Yeah? Okay, slugging, I think I gave you a picture, or not? Okay, we can take that. Okay, intermittent flow or also slug flow. Slugging, also that's called slugging, and the cause of that is just because of the dynamics of multi-phase flow. Okay, multi-phase flow just because at that particular combination of superficial velocity, liquid and gas, the most stable flow pattern is just log, unfortunately. Okay. Also might happen that you have transients. Okay, that for example you have accumulation, liquid accumulation. Okay. And that might happen in contrast with wax and hydrates. You might have also slugging. Sometimes it's not very common, but you might have it in wells, especially because some well trajectories, they are deviated and they go up and down. Okay, so they have also some areas where it's actually not exactly horizontal, but you have kind of a curvature, and then you might have liquid accumulation in the lower parts, and you have kind of a unstable or transient operation. Okay, and it can be because of two things: the dynamics of multi-phase flow, or just because you have accumulation. You have accumulation, pressure buildup, production, then again accumulation, pressure buildup, production. Okay, accumulation, then we have pressure buildup and production. Okay, or people also call it blowout, but it's not the blowout from drilling, but it's a blowout of the liquid blowout. Okay, I think there are some videos, some nice videos on the internet, on YouTube. Okay, I think, I'm not sure if you have seen that, but that's actually for it's done here at the energy department, this course on multi-phase flow that I told you. So you see that you have the liquid cannot go up on the riser. That's the riser, this is the seabed, and here is the production platform. So you actually, the liquid begins to accumulate at the bottom of the riser, and of course in this point the pressure begins to increase at the base of the riser, increase. Okay, until it's enough just to push the liquid, okay, and push it forwards all the way to the processing facilities, to the platform. Okay, and there are also quite a lot of other nice videos that you can take a look. Okay, so you have accumulation, liquid accumulation, pressure buildup, and then you have kind of a blow by where the gas comes in a plug and actually flushes everything that is in the system. Okay. So problems that we can get because of that is unstable operation. Okay, remember, we don't like that too much for the processing facilities, separators. They are expecting some amount of liquid to come, and when they get more or less, it's kind of a hassle. We have also added pressure drop. Because of this intermittency. Then we can get vibration, and that vibration can lead to structural damage. Okay, and structural damage can also lead to leakage. Okay, can create leaks. Okay, in pipe connectors, can create fatigue, can create a lot of issues. What kind of measures are implemented by the industry? Preventive measures and also solutions. As I told you, it might be gas lift in riser base. Okay, you have your riser going up, and then you put a valve, and you inject gas at the base of the riser just to stabilize and to be all the time sure that the gas will carry the liquid up. Then another option that is often used is choking at a riser end. Okay. You put a choke here, and then you choke to control the slug flow. And also another option that we didn't mention yesterday was you can also do a separation, subsea separation. Okay, again an area under development that but you might, in theory, if you have problems because of having these two fluids, you can just separate them, having the liquid and the gas separately, and just pump them and just transport them separately. What kind of tools are used to model this problem? Just transient, multi-phase flow, simulator, and in that case I already told you, Olga or Leda. And we are interested in seeing the slug frequency, slug length. Okay, if it's a big slug, very seldom. If it's a small slug, but more frequently. Of course, to see also the excitation, to see forces, to calculate forces on structures. Okay, and to force on structures, we usually there's a software called Riflex. Okay, that is to analyze sections of pipes, segments of pipes, and there is also another simulator developed by Marine Tech called Risana. I think it's with 2S. Riser Analysis Software, I think, and yeah, and we can use also, for example, finite element methods, finite element analysis, FEA. Okay. I'm running out of page, so but we are almost finished with this table. So we have then another problem that is called scaling. Okay, and scaling is basically happens when you are producing water from the formation, water from the reservoir, that this water has a lot of minerals. Okay, it's, for example, brine water from the reservoir, and all of these minerals, also due to an equilibrium of the mineral, the solubility of the mineral in the water, it might come out of solution and it might just deposit in the pipe walls. Okay, so we put that here, deposition of minerals from the produced water. Begin to deposit at P and T conditions. Okay, so in that sense it's very similar to the wax and the hydrates, but also it might happen because there is an incompatibility. You're mixing two waters that come from different sources, okay, and they have different minerals, they have different properties of carrying that mineral, but when you mix them together they are kind of incompatible, and that causes some scale deposition. So mixing of incompatible incompatible waters. They have different minerals, they have different properties, and when you mix them, some minerals that are no longer in equilibrium, they are going to just get out of the solution. Okay, what kind of issues might we get with scale? Scale also happens in wells. Specifically, is very important. It occurs in wells, and it's one of the main issues in wells that are producing water, some associated water. Okay, and what kind of problems it might cause is just going to cause cross reduction of the cross section of the pipe. Okay, but even something more important is that it's going to affect the place where this scale locates. Is mostly most of the time, or is sometimes, is on valves, on movement, on components that are supposed to open and close, like the gate valve, the swing valve. They also cause problems in the subsurface safety valve, so cause malfunctioning of well equipment. Okay, actually, sometimes there are quite a few wells in the North Sea that they have problems. The subsurface safety valve is not operating properly. Actually, it cannot close just because of scale problems. Okay. What kind of solutions the industry uses for that? Chemical inhibitors. Okay, to avoid scale deposition. Also chemical dissolvers, like in the case of, you can live with formation of scale, but after some point you have to you put the dissolver to remove the scale of the well. Also, remember that for all the others you can inject just at the wellhead. Okay, you don't have actually to put a line inside the well to go inside and inject. For wax and for hydrates, it's enough that you put it from the well downstream. Okay, but for scale, if the scale is happening actually in the well, you will have to put a line that goes all the way down to the bottom hole. Okay, I'm not sure if you see the difference, but for the case of waxes and hydrates, okay, if you have your system like that, it's just enough that you take a line and you inject it here and you inject it here. Okay, just from the wellhead. Okay, with scale, you have to actually, if you want to do chemical treatment, if it's very bad, the problem of scale that you have actually to, on the well, the formation, okay, that's the wellhead. Okay, you actually have to take a line down and put it here. Okay?
What do you mean by take a line?
You actually have to put this chemical injection line and put it inside the well. Okay?
You can do this wide line?
So, yeah, so that's if you want to have a permanent chemical injection. Okay, so many people, instead of adding inhibitors, they're taking dissolvents and they stop the well with certain frequency and they just dissolve the scale that it has to avoid having a permanent injection system of chemicals, anti-scaling chemical system. Okay. What else? Also can have mechanical removal. Okay, when the problem is too bad, okay, that you cannot open the valve, then you might almost use like a small drilling bit to mechanical removal, okay, to remove the scale, to open the cross-section area. And also it has been proposed pipe coating, okay, to avoid the deposition of scale in the pipe walls, to avoid that they will attach. How do we what kind of tools do we use? Just laboratory tests. Okay, laboratory tests, and we get from here also deposition rates. And then we go to our last problem. I hope I have space for that, or at least the problem that I'm going to mention here, that is erosion. Okay, and the erosion might be because of liquid droplets in the gas. Okay, gas traveling at very high speed, and then you have these liquid droplets that are impinging, they are hitting the pipe wall. Then you have gas bubbles in liquid. Okay, or the main culprit usually is sand production. Okay. What kind of problems that might cause? You have structural problems. You might have formation of leaks. Okay, you get also vibration. Okay, on pipe components. What kind of solutions people are using? They use special high resistant coatings. Okay, just a cover is kind of a protection layer inside the pipe to cover and avoid erosion, reduce the rate of erosion. If you see that you have a very severe erosion problem, then you try to, if there is a very abrupt change in direction or very abrupt change in geometry, then you try to smooth that geometry. For example, if you have an elbow, okay, and then you try to smooth, so you are sure that you won't have that the erosion, the velocity at which the sand particles hit the wall, they are not high enough that they can cause problems. So modify geometry. And this is usually, you have these bends usually in jumpers and in connectors between wellhead and template, and that's where you can put these modifications. And also one thing that we don't like too much, but that is very effective, is to reduce the flow rate. But that's really the last, and some fields they just don't have any choice, okay? They just have to reduce the rate. They are just producing too much sand. It's causing too much erosion in the system, and if they continue producing like that, there will be a leak and there will be problems with the integrity of the pipe. So they have no choice but just to reduce the flow rate. They reduce the drawdown in the formation, and then it produces just less sand, okay? And there is really no solution, but we don't want to get to that position. And also there is sand separation, subsea sand separation. Okay, subsea, that it goes in the same category, has subsea separation. It's something that the service companies, they propose. It looks like a very nice idea, but still operating companies are not using it at the moment. And here the tools that you have to analyze erosion are actually you use a lot of computational fluid dynamics. Okay, that's called CFD. Okay, and the idea is that usually for all the calculation that we have been doing here in class, we are using kind of a one-dimensional approach. Okay, the flow is represented by one velocity, by one pressure and one temperature. In this approach in CFD, you want to see actually the 3D of the flow. You want to see every detail. Like if you are analyzing an elbow, you want to see exactly how is the velocity profile in the pipe. Okay, and you want to see exactly how that velocity is going to change in the geometry. And for that you need a kind of a very high defined solution of the flow in the pipe. Okay, so for that it's called computational fluid dynamics. Anybody work with CFD before? Here? You? Okay, so you're the expert. Huh? Yeah. Okay, I remember also that this analysis of all of these issues, we are not putting it because we see in time, for example. Okay, you have the Q of the field with time, and let's say that we are producing in plateau first and then we go down. Okay, so really we are not like in the previous case, or what we have been doing so far is that we try to couple reservoir with production simulator. Okay, in that case we come at some particular points in time of our asset. Okay, if we are in operations or if we are in planning, and we come here and we execute an analysis at that particular point in time to see what kind of transient problems I'm going to get, if I'm going to get too much erosion. So I do the analysis at one particular point in time, and usually I don't solve the whole system, but I impose the rate. Okay, I impose, for example, this rate that it will be producing, I impose it in the system, the same way we have done in Hysys, and from there I calculate what might be the temperature reduction, if I'm going to have any transient, etc. Okay. Okay, so I go at that particular point in time, select it, and that's where I execute the analysis. And I do this both in the design phase and I do it also in the operational phase. So we take out all the complexity. If you go to a flow assurance engineer and you say, oh, coupling, reservoir simulator, which reservoir pressure you're using, they're going to think this guy is crazy. Why is he talking about all of these things? Okay? Because they just don't care. They look at one point in time, I know how much I'm producing, I know how much my rate is, and then I impose on the pipe, and then I perform my analysis on the pipe, you know, I execute hydrates or wax or transient, etc. Okay, and they don't care about interaction, flow equilibrium, well performance, etc. Okay. Any question? Okay. So we can consider this topic finished. Then was just to give you a taste, and we are going to talk now about in this short time that we have, we are going to talk about production enhancement techniques. Okay, and we are going to start with the particular case of ESP that all of you should learn this abbreviation. That is electric submersible pump. Okay. I think I have some figures. Okay. So the ESP is basically a rotating equipment, okay, a pump that we put as part of the. Let me see if we can. Like that, okay. An equipment, a rotating equipment, like a pump, okay, that we use in our normal life. A pump that we connect in the tubing, and the idea is that it will boost or give a pressure increase or give more energy to the fluid to be able to flow from the bottom of the well all the way to the top. Okay? And you already have some idea that if I do my equilibrium, let's say I do it at the bottom hole pressure, okay, I have a Q of oil, and then I have the available and the required. If I want to be producing here, then I have to put something that bridges that difference. It's just like the choke, but the opposite of the choke. I want to put the pump is something that is going to bridge and give me this delta P. And really this discussion is just to tell you what things do we have to take into account, because the pump has certain operating range, okay, has certain operating conditions that you have to fall inside of this operating map. If you, for example, your combination of rate and delta P falls outside of this map, then you won't be able to give that delta P at that rate, okay? And then you have to go back, select another rate, and get another delta P and check if that point falls inside or not. Okay, so we're going to have a short discussion on that. So the pump, the structure of the pump is we have the tubing, okay, and the pump actually goes threaded in the tubing, and the pump consists, the electric submersible pump consists on the pump section. At the pump section, I have a picture here, okay, how it looks like. Okay, the pump section is actually, you have it here, okay. So it has one part that goes rotating, that is the rotor or the impeller, okay, and the fluid is going inside. Actually, I can show you okay, it looks like that without the cover. If you remove that cover up here, okay, you will see exactly that. Okay, So it's rotating, the fluid is coming in the inner part and then it's exiting through the outer part. Okay? And that's what's giving this change. When the fluid enters into the middle part, it has some velocity that is given by the rotation rotational velocity of the disk. When it's exiting in the outer part, it has a different velocity, which is higher. And this difference in velocities in this diameter and in this outer diameter is what causes the pressure increase. Okay? And then goes, that's rotating, the fluid comes out of here, then comes inside. Okay? It's just going out, back in, and then it's entering into the next impeller. Usually a pump is not made only by one impeller because this cannot increase the pressure very much. Okay, it's only a little bit, but you have an arrangement of maybe 60 or 80 of these in a pump. Okay, so I'm going to pass this down so you can see how it looks like. And we are going to put this okay, and that's the impeller, and the fluid is coming through here, through the center. You see here the opening that you have, you will see it soon, and then the fluid is passing in this interspace and then it's coming out of here. And this difference, if you see here you have when it's rotating at a certain rotational speed W, and you have certain radius R1, okay, you have a velocity U1 that is R1 times W, okay, and then you have at this point at the exit diameter you have a greater radius, so the velocity will be greater because W, the rotational speed, is constant for both points. Okay, and this is actually what is giving you the increase in pressure. So in the pump we have different sections. We have the pump sections, which are stacked. They call it in kind of a pancake of pumps, okay, one on top of the other. And then you have, in case we usually, the pressure here in the suction of the pump should be undersaturated. Okay, so I have only liquid coming inside the pump. But if for some reason the pressure drops, remember the pressure is declining with time. So sometimes it's equipped with a gas separator, okay, that it impedes or avoids that the gas will enter into the pump. So one question is, what do I do with this gas after I separate? It's going to stay there lingering all the time?
Maybe it will bypass.
Okay. If I'm expecting some gas from the formation, I have to leave the annular space open. Okay? And then I have to produce the gas through the annular. Because otherwise I will have accumulation of gas and then it's going to go through the suction of the pump and then I just have gas in the pump and I'm not pumping anything. Okay? It doesn't work properly. But if I am lucky enough that the pressure here is undersaturated, so I will have only liquid coming into the pump and really I don't have the problem of production of gas production. Okay? And then I go back down, continue down on the pump, on the ESP, and then I have a seal section that this is separating this rotating part and the pump part with the motor. This is actually what is moving the pump, an electrical motor. Okay? So from here it has a long shaft that is going up and is engaging. If you see the rotor, it has some kind of on the inner part it has a hole. Can you see it? It looks something like that. Yeah? Well, actually at the opposite. Okay, has a small incision like that. So that's to support the axis, and the axis is to give rotation to the impeller. Okay? So here it has the shaft going up and rotating the pump. So how are these pumps, or what is the performance? Remember, all the time we are concerned about what is the performance or the operational envelope of these kind of pumps. Okay? So the performance is very similar to an IPR. Okay? hydraulic performance of ESP is very similar to an IPR. Is that the delta P across the pump and the rate, and actually this rate is the actual liquid rate. Okay, so that's a big difference. This is not available pressure, but this is delta P across the pump, and this is the actual liquid rate at pump inlet. Okay, how does it look like if it's similar to the IPR? Like that, okay? And if you, those of you who have a background in pumping, you might know the why it looks like that, but I'm just going to tell you that it's kind of a conservation of energy. Okay, if I produce a very small rate, then I'm able to create a big delta P, a big pressure drop. Okay, but if I want to pump a high rate, then the delta P that I will be able to lift is not much. So it's kind of an equilibrium. I can get either a lot of rate but low delta P, or I can get a small rate but high delta P. Okay, it's kind of an energy conservation along this line. Okay, and this line is for one particular rotational speed. Okay, for F1. The rotational speed of the pump, it comes given in hertz, and they can go from 90 hertz, that's the maximum really that the pump can run, all the way down to 30 hertz. Okay, how much is that in RPM? That will be homework. Okay, so you also, that thing that you learn in physics to change from hertz to RPM, you say, I'm not going to use this anymore. And then you come to field development and you say, oh, again, this guy is asking about these things I forgot a long time ago. Okay? So this is for a fixed frequency. What happens when I change the frequency? Okay, and so I'm saying that this pump is a combination of stages. Okay, it's a combination of these impellers. Okay, that actually have 60 of them, I told you, going out, then back, pumping out, back, and so forth. So this curve is for what? Is for one impeller or is for the whole pump? For both. Okay, I can do both. Actually, to find the performance of a bunch of impellers, I just add them up. Okay. Okay, delta P and Q. Okay, and I have for one impeller, okay, for another impeller, for another impeller. Okay, so I go and add them up one by one, and then here for example I have 3, and I add all 70 of them because there will be flowing the same rate through them, right? All the time the rate is the same, so the rate, there is no change to make here. I'm just going to increase the delta P is just going to be the sum of each one of the stages. Okay, so I think I have a real picture here of the performance curve. Okay, like that. So this is how it looks like. That's local flow rate, local liquid flow rate. Okay. And here I have head, which is the delta P divided by the density times the gravitational acceleration. Okay, just the way it's the same delta P, but it's exactly the same figure that we got before. And you see here it goes from 90 hertz, that's the highest, and that means because if rotating quicker, then the pump should be able to lift a bigger delta P. Okay, if it's smaller, then the pump, and you see it's quite dramatic, it's kind of 7 times the difference in delta P. Okay. Yep, and think don't have much time. Yeah, we can talk about okay. How do I get this variation of how do I get this variation of rotational speed in the rotor? I need a special equipment, so I get for each one of the pumps I need a variable speed unit. I take either from the grid, from the national grid, or I can also use a diesel generator, local diesel generator, and then this one determines the this one changes depending on the frequency that you want to get in the pump. Okay, converts the current to achieve exactly the rotational speed that you want to get in the pump. Yeah, I think it's better to stop here to ask you if you have any questions, and we continue next week. And we are going to make one exercise about pump, about the ESP, and then we are going to move to compressor to give you a background about compressor, and then we're going to talk about design of boosting for in the life of the fuel. Okay. So before we finish, any question? Yes.
This wiring. So we have the electrical wire inside the completion, or it is outside.
Yeah. Let me show you. I think we had a picture. Yeah, I showed you some pictures about the Rubiales field. Do you remember? Okay, actually it's here. Okay. Okay, you see the cable going inside of the well. Okay, that's the power cable of the pump.
Inside tube.
Inside the, it goes inside through the wellhead. Okay.
But it's outside of it. So it doesn't like.
It's outside of the tubing.
In the annulus?
Hmm?
In the annulus?
In the annulus. Okay, and actually the unit, I don't have it here, but it's on the other side. The variable speed unit is not here, but it's actually on the other side. Okay. Yes. Any other question? You're not going to forget about pumps on the weekend? You swear? You promise? Huh? Okay. Remember, very similar to IPR, but delta P and rate, okay, going down. And the reason for that is I can get either high rate or a small delta P, or a small rate but high delta P. Okay, there is some kind of energy conservation. And as I increase the frequency, that curve is kind of amplified, okay, going up, scaling up. And we will see later that the point that you want to find, you get a rate, okay, and you get certain delta P, and you have to, the point has to fall inside the operational region of the pump. We will see that it's not possible actually to operate in all of this drawing, but there will be some areas that we want to honor, and we will see why is that exactly in next class. Okay, why do you have to operate within certain region? Has to do with efficiency, has to do with maximum rotational speed, has to do with some other things. Okay. Okay. Any more questions? No? Okay. So see you on Monday.